Without further ado, let's start with the keynote session. Dr. Victor Bahl doesn't need any introduction. He is extremely well known in our research community. He's a Microsoft Technical Fellow and CTO for Azure for Operator. He has led research in a wide variety of topics, such as 5G, edge computing, live video analytics, mobile computing, wireless system, cloud services, and data center networking and management. Over his career, he has built a number of seminal, highly cited systems, published prolifically in top computer science conferences and journals, and authored over 165 US patents and given close to 6 keynotes. He received numerous prestigious awards and honors, including AAS Fellow, ACM Fellow, IEEE Fellow, and 4 Lifetime Achievement Awards. He has engaged in significant professional and company-wide leadership activities. He just gave the keynote speech at MobileCon in Australia last week. For those of us who couldn't go to Australia for MobileCon, he will give us a special treat today by giving a special edition of his keynote speech on cloud-based telecommunication infrastructure. He will discuss both business opportunity and research challenge and direction in this exciting area. Next, I will hand over to Victor for his keynote presentation.
Thank you very much, Lily. You guys can hear me and you can see the slide?
Yes.
Okay, thank you so much. Yes, I did just come back from MobiCom. In fact, I just flew back today in the morning at about 12:30, 1 o'clock I landed and I'm here. So this talk is, if you saw that talk, then this is the same talk, except it's shorter. But I just sort of like picked a few materials from there and doing it. So I also changed the title a little bit, but it's effectively the same thing. So let me begin. Let me time myself so that I don't go overboard here. Okay, so let me start by sort of like going through a little bit of history of how we got here. Okay, so in 2008, I invited 4 other colleagues to the Microsoft Redmond campus to discuss and to have a whole day of discussion on what happens after the cloud. Now, the cloud was already starting, well, it just started to take off, and then they were, people were already starting to understand what it is and moving in that direction. But, we are in research and we have to think in advance. So, for example, you're going to hear about the Edge in Space story today by Ranveer and Shadi and many others. So I invited these individuals and we sort of like sat the whole day, we out at lunch and we talked about what would be the next thing. And the next thing, cloud was going to sell us storage and compute. Compute and storage. And we wanted to sell a delay. Now, the issue with delay is that it's the internet that is in the middle and it's hard to take the internet. So in all our discussions, we conceived of what that has now become edge computing. So that was about 13 years, 11, 12, 13 years ago. And we just recently actually got a Signal Tester Time Award that you see as sort of a picture of here. So anyway, that's how Edge got started many years ago. And there's a lot of story here about like how I tried to sort of push it into Microsoft. I gave 2 talks in the Disruptive Technology Review to the SLT, and we went back and forth on it. But 2017, Microsoft took it up. But in the meantime, I was a researcher going around. So this is a sort of a slide I took from a presentation I made in 2013, and you can sort of see I made a prediction, which is usually very not a good thing to do, but I did, and I said by 2020. This is how the world is going to look. It won't be just the cloud, it'll be also edge. And voila, it actually worked out to be that. And there are many documents. There's an interview I gave, and this is also there in 2015, which describes how the world will emerge and how it will become, and it has become that way. So I'm sort of, pretty proud of it. Then one of the things that happened was that when I tried to push it with Microsoft, there were a lot of discussion about the cloud being only 20 to 30 milliseconds, maybe even less than milliseconds away from every paying individuals on the planet. And so the question was, hey, if you're going to be 20 milliseconds away, why do you need another edge device? So I gave them lots of reasons for it, but it became a sort of a discussion. It was sort of, I knew that I had to show them the money, where the money was. And so I decided to sort of embark on video analytics because I thought video analytics will be everywhere. Especially, I know it's very prevalent in China, it's in the UK, it's in the US. So it was really everywhere, and that's where the edge would shine. And so we wrote this paper, that edge real-time video analytics is the killer app for edge. I mentioned this because I'm going to say it again later. Okay, so then there were other things. There was this National Electronics. They said 2019 was the year of the edge compute, and they interviewed me, and I said many things that I'm going to actually say now again. So so there'll be another set of predictions that come out of all this stuff. All right. So now, I mean, if you sort of look around, there are thousands and tens of thousands of edge articles of edge on any of the search engines. You go to Bing, you do. And also, like, companies have come up with all kinds of applications in different sectors, from transportation to manufacturing to retail to energy, and just about everything has an edge application there. So it's taken off from that perspective. So that's all good news. Now, the academic forces in the United States were a little slow at this. They sort of like didn't know what to do with edge. They didn't know what was different about it. But like I said, this journey started in 2008. Excuse me. And now in 22 and 21, the NSF started a series of national research centers. I'm actually on the advisory council of the two of them that deal with edge on AI and edge. So they had decided that there was something different about this. They had to do some, they had to get the academics to move forward. And so they funded these things. There was also a RINGS project that's got started with about $40 million of funding, and Microsoft is participating in that as well. And then Intel also started a project with NSF with about 30 projects or so, and I'm on the advisory council for them as well. So my point is that academia also started down this lane, but it was a little late from where the industry was. Okay, so that's the other thing that happened. And so I started with 2009. The other thing that happened is right where you are in Beijing. On April of 2010, we had sort of a workshop in which we talked about the SORA project. Now, some of you may remember, or some of you might not. So SORA was the software-defined radio project that came out of Microsoft Research Asia, or Beijing at the time. And then, and it was a great project because even though the community knew about software radios, it didn't have a system that operated with commercial Wi-Fi engines. So these guys, the leader of that project is actually here in Redmond with me now. He's working on the new stuff. But they built a system that operated with commercial Wi-Fi, and that was phenomenal. And not only that, they then started to give the system away to many universities around the world. Now China Mobile noticed all that, and they wrote a white paper based on what SORA had done. And the white paper was the start of CRAN, Cloud RAN, which is the topic of this meeting today. And they sort of invited Microsoft Research along with a bunch of other companies to come and form a consortium to work on CRAN. And these are the companies that joined. Microsoft Research decided not to join at the time for various reasons. Now, the CRAN project took on its own shape and sort of like came to the US, and Alcatel-Lucent and these folks tried to do something, but it didn't actually go anywhere. It just sort of like in a few years died. But nevertheless, the CRAN vision came from there. Okay, now set that aside. I want to talk to you a little bit about, and I'll bring it all together. So I want to talk to you a little bit about the global network that Azure operates. Azure operates one of the planet's largest global network. This slide I've been using for many talks. So if you've heard me talk, you've probably seen this slide. And so we have 62 regions. Each region has multiple data centers in it. And we have about 175, probably 180,000 miles of fiber that interconnects them. Now that's a pretty large network. Now this, like we have millions of miles of fiber connecting inside the data center. This is between the data centers. Now we have hundreds of terabits of capacity available. We use a very small amount. We have about 50 terabytes, and these numbers change all the time. So just sort of look at these numbers as just to give you a sense of how big the system is. My point here is that we have a very large system. It works really well, and it moves packets around the world, and it is not so much dependent on the internet. And then the rest is just sort of numbers to sort of give you that point. Now, not only do we have that, we also have a satellite network. We have gotten into the satellite network, and I think Ranveer and Shadi are going to talk a little bit about it, so I wouldn't actually believe at that point. But nevertheless, we have just where I sit, we have a sort of a sister group called Azure Space, and they started off by building ground stations for satellites. The idea of that was that as the satellites move, the ground stations would pick up the data and then move it around the terrestrial WAN network, so giving the impression of a much larger global network. And we are also starting to now send, I don't actually want to say much about that because I don't know how much I'm allowed to say, but nevertheless, we are into this business of using both satellites and terrestrials. And there's just a picture, ad hoc picture put together. But the point of this is that the combination of the two forms the backbone network, the global worldwide backbone networks. And of course, there is a lot of research to be done here, which I don't have the time to go through. But you can just sort of imagine that we are taking a network that exists, which has access capacity, and it has different kinds of infrastructure, and we want to repurpose it or reuse some of that capacity for next generation communications. So now this brings us to this picture, which is the one I actually shared with the CEO of the company, Satya Nadella. And this is a very simple picture, but I kind of like it because he just spontaneously asked me to present, and I didn't actually have any time to come up with anything major, so I came up with this, and I like it. So what this shows is that if you take a cellular network and base stations, you have edge computes, and then you have Azure operators. And what the idea here is that, look, we can actually do everything now that, for example, in research, we've shown this multiple times that we can do everything in software on vanilla hardware. We should be able to put this whole thing together and offer this as a service to the cloud, to the telecommunication network. So I talked to you about Edge, and it's been, like I said, 12, 13 years, and we have a very heavy investment. Microsoft has a very heavy investment on Edge. I talked to you about the CRAN project, that's how it started and how Microsoft actually participated in the original sources of the RAN thing, which has now become RAN. And then I also talked to you about the Azure for operators and Azure network, which is a global network which we have available with access capacity. You put it all together and you have an alternative infrastructure for the telecom. Now, why would the telecom take this? The reason they would take it is because they, in the last 5-10 years, have tried very hard at the C-level, have tried very hard to make more money from their networks because they are the ones who bring the customers over. But it's very hard to monetize a network. I mean, they spend billions of dollars and we spend billions of dollars, but we don't monetize our network. We monetize the services on top of it. But we have the network and we need it for our services. So the idea is that why don't you just use our network? I mean, just like what the cloud did to the rest of the world, we can do the telecommunication companies as well. So just saying, hey, use us, you maintain your customers, you maintain all your services, and we will help you reduce your CapEx, OpEx, and also will help you increase your revenue. So in MWC 2022, so anyway, I moved after this thing. The CEO asked me to move, and I moved from research after 23 plus, almost 24 years in MSR. I moved over to a product and became a CTO of that division. Now, in 2022, MWC, we actually announced these 4 projects. So the most significant one, and from my perspective, is the AODS, or Azure Operator Distributed Services product. I'll say a few more things about that in just a minute. We also bought a couple of companies. We bought Affirmed, which was the top level company in mobile core, and we bought Metaswitch, which was the 40-year-old top level company in voice protocols and things. And so we put them together and created products out of it, which we now sell. And then we also created, from the edge perspective, we created what is called private 5G, and with the core, and now we also have a thing called public MEC. So there's a lot you can read about it in there's press and different blogs about it, so you can learn about it. So this is what we announced. Now, Azure for Operators is one of the main project we are doing is AODS. Now, this slide is busy. I recognize that, so don't worry if you don't get all of it. But the idea is that AODS is the framework on which network functions can operate. So now think about it this way: that you get a bunch of servers, they're sitting, and then you you say, okay, what now? So AODS will now basically connect them, create the fabric, connect it to the Azure management framework and all that stuff, and then allow you to put whatever network functions you want to put on that. And this is what the operators want. They want the flexibility to put all kinds of network functions in it. Just looking at this picture, so the top level is the control plane. This sort of talks about the various things that AODS does, and then on the bottom is like the near edge, the far edge, and the public Azure MEC, and they are parts of the AODS runs on it. Now, this is one of the very main product, and it's actually a good product. Now, one of the beauty of working with Microsoft is that Microsoft has Azure, as I said, and has the network, and they have done tremendous amount of work, as you can sort of see in these pictures. So the idea is that if you go with Azure and we build all the holes, then you can plug any one of these services into your system. So you can sort of like work with Azure Streaming Server, for example, and analytics, or you can work with Azure API for management. And so you can, these are all well documented, well run services on Azure that you can plug and play, and you can bring it to the operators, who didn't have these services. And so that's sort of a sample dashboard that I'm showing here. Now, another thing in the wireless or in the centers that I talked about, and AI Edge, I talked about how many professors, at least in the US, and I'm sure this is true in China as well, are working on AI. In fact, every student wants to work on AI. So there is a lot of work going on. And so the question is, how do you plug all that information, all that knowledge into this large network that we're creating? So AI Ops is one way to do it. AI Ops is just a term that we use. So here's an example of the things we actually use in Azure. AI, and this is a very short list because I didn't want to fill out the slide so that you couldn't even read it. But here, so that you can start to see that we use AI for. Oh, my light went up. Anyway, we use AI for failure detection of hardware, for chip failure detection. We also use it for managing capacity, predictive analytics on increasing the sort of the resources that you have given, so resource analysis, and then all kinds of like other stuff that is very important for getting your system to work properly, and all the things that we are doing. All the centers are doing are also fine. We can actually start to use them because we have this AODS framework, we have the network functions, and we can actually put a lot of this stuff. So if you're a student here and you're working on some AI, an idea to improve something, come and talk to us. I mean, there may be a way for us to sort of plug that in. We are doing our own as well, as I've sort of shown. So in my group, when I moved with about a few researchers. They all have PhDs. They all work for Microsoft Research. So pretty top level talent. And we created these work streams. And I just sort of show you how we ourselves, like I am operating within the context of where I am right now. So they're not orthogonal to one another, but for example, RAN analytics and Cloud RAN are kind of similar, but we call RAN analytics out because it's sort of, you can do this independently if you're building your own RAN, as an example. But we also have this global WAN, which I talked to you about, which is about, we want to repurpose or redo it. Like one idea that we are pursuing very aggressively is the virtualization of the WAN. If you virtualize the WAN, then you can give it away to the operators. Another idea we are pursuing is, but by the way, in the virtualization of the WAN, there are many important things like verification services. I mean, the idea of virtualization is that the operator will say, okay, well, I have this WAN, and will make the changes. And then the verification system will actually verify that that changes are possible before going down to the physical system, because the physical network is actually being used by Azure as well, and so we don't want to disrupt that. So that's sort of where virtualization will fit in. There are other things too. Analytics will come in there as well, because they want to know how the network is doing, and so we do the analytics and provide it to them. And then, so that's this virtualization. But then there's other idea we're pursuing aggressively is like operators have spent a bunch of money on their WAN, and we're spending money on our WAN. And so can we connect the two together to create a much bigger WAN? So, where their WAN and our WAN comes together. But there are problems. There's problems like people don't want to divulge to us how their WAN is working or what is happening there. So, one has to sort of build systems that actually can work even without that. So anyway, that's the 5G WAN. Then there's a verification. I just mentioned that. There's also programmability. We are actually doing a lot on that. For example, network slicing is a term you must have used. It's used, but the actual implementation of it and how you use it is an open question mark. So even when people write papers on it, they've never addressed that part of it. So, but we are looking into that. We're also looking at, all the operators actually provide programmable networks, and then they want application writers to write it. But application writers don't actually go and write for each individual network. They want to write generically and then have it operate in the other places. So we're sort of addressing that as well. So there's a lot to do in programmable, and this is a different world than the world we have actually inherited or worked with in the past. Then there's EVS. This is the video analytics stuff that I talk. I'm still very passionate about it. We've written 30-some plus papers on this subject, and I think this is still a killer app within quotes. And I say that and more. Then the security has changed. Everybody cares about security, and then there's obviously new hardware that is coming, so we care about that as well. Now, so to just sum up the RAN thing, so I think RAN is now the killer app for the edge. So when you think of edge, every packet that goes will go through the edge, and that is where RAN RAN is a radio access network that'll operate. It's also a multi-billion-dollar opportunity. That's because it's going to be everywhere, and everywhere means a lot of money, and this is serious computing power and computing storage. So it's sort of everywhere. It also helps, like this whole thing about offloading, reducing CapEx, OpEx, increasing revenue. It sort of helps in that as well. And we as a company are focused on not about just like, oh, we are the ones who know how to build it best. We are happy to work with anybody. If you guys have a great RAN that you've implemented, we'll work with you, or otherwise we do our own thing. Okay. So just a very, very quick thing here, and then I think, yeah, let's see, I have 15 minutes. Okay, so this is how the old networks used to work, right? There was sort of the base station. I'm sorry, there was a radio, a cellular unit, then there was a base station. Actually, if you went, I know in the US, I know this is true, I'm sure it was true in China too, you kind of went to these cellular towers, and on the base, there would be a sort of a shielded area where servers would sit. So right on the cellular tower, the servers would sit. And the BBU, which was the baseband unit, a processing unit would be there, and then it would go to the core somewhere. And then, so this has changed radically in 5G and now 6G and 7G or whatever, right? They have busted open that whole system into many, many components and many, many software components. They call them DU and CU, DU distributed unit, CU centralized unit. And they have started the idea of near edge and far edge, near edge to the cloud and far edge from the cloud. And that's where they put the servers, and that's where everything happens. And you can actually, the spec, if you read the spec, it says within 20 kilometers of an RU, you can have your first piece of hardware. So you don't actually have to put it near the cell towers. And part of the reason is that we are using many, many different frequencies. And so now the density of these systems increases. And so, just real estate is a problem. And so they just kind of want to do the wire thing. So this is what has happened, but this has actually helped all the software giants to now come in and do their thing. Okay, so this is just this is a research talk or to talk to researchers. We don't actually think about these things, but now that I moved from research, I have to think about these things. So here's a sample. Again, this is not a completely, comprehensive list of companies, but just to give you an idea of how many companies are doing how much in these small spaces. Like if you take far edge, you've got all these other companies listed here. If you take near edge, you got all these companies listed here. So there's a lot going on, and there's the reason I sort of told you the story about the edge computing in the past was because the academics completely missed that one and took many, many years before to come. And I kind of don't want people to miss this one as well, because yeah, it doesn't matter to me, but like I don't want to lose 10 years of my time before this thing really takes off. But anyway, so the point is, this is huge, even though you sort of think about, future research and future things, but this is now, like this is happening now, and it's not there, like in the sense that this is the future. The world is going to look very different when you move forward, and then many of you will realize it and then kind of jump into this. So that's the sort of purpose. Now, we did some hard work here. We, I wanted to tell you that we are not in the business of trying to sort of like do everything, or, we are the ones that can do most of the muscle and all. We are happy to work with anybody. So what we did is we looked at the companies and sort of like from those companies decided what is it that we will build. So the red is in that. And then what is it that the partners already have? So for example, the L1, which is sort of, the layer one, has LDPC and FFTs and things. We can build that, but it's already built, so why do it? Similarly, L2 is the Mac. We can do that, but it's already done, so why do it? So this is kind of like a sort of a picture of that. I just wanted to give you a sample of how we think, how we work, and how you might want to work as well. Here's a little example. I'm going to show you a little video of what we do in software. So here's an example of 3 servers. 2 of them have this red, which is very highly congested servers, and then you have the less congested servers. So because of the beauty of software and AI and ML and all that good stuff, what we can do is we can do load balancing. We can move things around in real time while they're operating to sort of increase the load. We can also do things like defragmentation and power management. We can shut off a server by moving things over to the other servers, and so that saves energy. We can also use that to increase the feature or remove the features of some features that we need to add on a production system. So we build a system, and here's a little video. I'm going to show you just a part of it. Let me see if you guys can hear it.
Welcome to a demo of Project Slingshot from the Microsoft.
Can you hear it? Hi, anybody?
Yes.
Yeah, we can hear.
We can hear.
All right, because I can actually see. So I'm not gonna, like I said, not gonna play the whole thing.
When an L1 server fails,
sorry, I just wanted to, because we did this for an internal thing. I want to go to, okay, let's start from here. Yeah.
Now that we have shown the technical details, let us see how Slingshot works in the real world. Our demo uses a 5G O-RAN testbed that we have built in Microsoft's Building 99. The CPUs and switch chip, as well as the FlexRAN Layer 1 network function, are from Intel. We use the remaining VDU and VCU network functions from Capgemini and Microsoft's Fusion 5G core. In the demo, a Raspberry Pi UE with a Simcom 5G modem will stream a video from a Foxconn radio unit with 4 antennas operating in the N78 frequency band. The RU's fronthaul interface is connected to 2 servers running Intel FlexRAN via a programmable switch. One server acts as the primary and the other as a hot backup for failover. The backup server is initially idle and has near zero resource utilization. When the primary server fails, Slingshot will automatically migrate L1 processing to the backup server. We use 3 other servers to run the VCU, the 5G core, and the video server. We first show how without Slingshot, a failure of the L1 network function causes severe connectivity disruption. The video on the left is a screen capture from a Raspberry Pi UE as it is streaming a video. And the UI on the right shows the user bandwidth handled by the L1 network function reported by FlexRAN. The video stops when the L1 crashes and the UE disconnects from the network. We can also see FlexRAN's throughput in the UI drop to 0 after it crashes. Our fine-grained video bitrate measurements show that the UE regains connectivity after 3 minutes of downtime if we immediately restart the entire vRAN stack manually. Next, we enable Slingshot and add a backup server for the L1. The backup server is shown in the lower half of the UI, and it starts processing user data after the primary L1 crashes. We see that when the primary L1 fails, Slingshot automatically detects the crash and migrates L1 processing to the backup server in less than a millisecond. We can visually see that there is no disruption in the video streaming. Our bitrate measurements confirm that with Slingshot, the UE's bitrate during L1 failure is indistinguishable from its bitrate in a failure-free run. Thank you for watching this demo. In summary, we have shown you our work on.
Okay, so
Welcome.
the reason. Okay, so what I skipped over the technical details of it, but just now the guy is Anuj Kalia. He worked with Dale. They're all researchers, and what they did is they used programmable switches in the front part of the system to be able to sort of move things around very, very fast so that nobody even noticed it. They also did some more innovation in sort of disaggregating the Mac from the PHY to put it on different servers. So there's some beautiful things in there that were done to achieve this thing. So that sort of gives you an idea of that. Now, the other thing I kind of quickly want to talk to you about is management. So, and the reason to talk to you about management is because this is what operators care about. I mean, they love the fact that, a company like Microsoft can manage Azure so well, and they want to be able to manage it as well. And then they want to bring in all the AI and the ML that we talked about and all the other stuff. So we took that up, and right now we are at about 30 minutes. Within 30 minutes, you can put up a cell site. Now that's pretty incredible. Others have shown it too, but we've got this technology as well to show it. And we connect it to Azure Arc. If you don't know what Arc is this management framework where you can use any kind of like heterogeneous servers, Linux or whatever, and it sort of connects you to the thing. So I mean, I have a lot to say, but I'm going to run out of time. So I'm going to again show you another video. It's about 3 minutes long. We actually created a new thing called KFO K8 extensions. Now, if you go and look at the sort of the industry, you will see that companies are coming together, creating consortium. Google just created some consortium, but they don't reach far enough. Here, we sort of took it upon ourselves to sort of think of more as the systems researchers and build something. So here's another video with Sanjeev. This is less polished, but nevertheless, it should be good.
At the Azure for Operators Office of the CTO team, we have been working on creating technologies to run virtualized RAN functions on the far edge using a distributed cloud platform that we have been developing. Although RAN network functions run at the far edge, the distributed cloud platform is able to utilize the power of Azure to manage, deploy, and monitor both the far edge infrastructure as well as the CNFs running on top of the infrastructure. When building this platform, there are two main challenges. The first is how to provision and monitor the infrastructure itself. That is, to go from bare metal servers to a Kubernetes cluster which is fully managed via Azure. The other is in developing a platform which can allow vRAN CNFs to be deployed as cloud applications from Azure, which will run in the far edge. This platform should fully automate the deployment, alleviating the need for any manual tuning of the CNF workloads. These are key industry-wide challenges which have been identified by ORAN's OCloud working group. To solve the first challenge, we have developed a platform using industry standards as well as newly developed innovative technologies which allow us to go from a collection of unprovisioned bare metal servers to an Azure managed Kubernetes cluster optimized to run vRAN in less than 30 minutes. We've also developed an analytics platform which can monitor and diagnose issues in the Edge platform and in the RAN CNFs. Here we see this cloud-based provisioning system in action. On the left is a console from a VM in Azure, which is remotely provisioning the far edge machines, and on the right is the console output from the far edge machines. The remote provisioning from the cloud is responsible for setting up a BIOS tuned for running vRAN workloads, as well as installing a tuned version of the Mariner OS, which is a fully open source Linux distribution for Microsoft's cloud infrastructure and edge products and services. After this, a Kubernetes cluster is created from the provisioned machines with their custom developed extensions for running vRAN. This cluster is then Arc enabled, allowing us to use Azure to manage the workloads running on the cluster. After the machines have been provisioned and the Kubernetes cluster is created, we then need to deploy the RAN CNFs onto the cluster. Current vRAN deployments require significant manual tuning of CNFs in order to function properly, making it impossible to scale. To solve this issue, we have developed an innovative platform to extend Kubernetes called Kubernetes for Operators RAN, or KFOR for short. KFOR solves hard CNF deployment challenges such as automatic CPU and device scheduling, allocation, and isolation, making vRAN deployments truly scalable. Using this workload provisioning system, we can now remotely install RAN workloads onto the cluster with a click of a button from Azure. The vRAN workloads running on the far edge for each base station show up as resources on the Azure portal, along with the associated pods on the Kubernetes cluster. The vRAN can even be deleted and then recreated from the portal. It also allows swapping of RAN components from different vendors using the same far edge hardware, platform, and Kubernetes cluster. This allows vRAN to essentially become an application which can be deployed, managed, and monitored from the Azure cloud.
Okay, so here's the thing about this amazing.
At the Azure for Operators,
this solid.
At the Azure for Operators Office of the CTO team, we have been working on.
The point is that RAN. Okay, think about RAN. RAN is the signal processing physical layer thing along with the MAC. We can just in live mode move it around. Like we can use Altron's RAN, and then we can switch to Radis's RAN or somebody else's RAN. Now this is powerful. I mean, this is something that never existed in the past, and we have done it through existing things like Kubernetes, which tens of thousands of developers know about. We extended it and we brought in some new tech, and now we were able to do this. I think so. If you're in the business of what I'm saying, or what you get it, you will understand the power of this technique and the sort of the flexibility it provides. So I thought I should mention that, and we sort of did that. Now I'm going to show you some really quick pictures. We have a project. It's called Project Cooper. And if I was live, I would ask you if anybody knows what that means. Well, because we are live, but it's hard to sort of interface. So Project Cooper is named after Martin Cooper, who's known as the father of the cell phone. And so I thought, this is just as respect to him, we kind of named that. So here's it's a very different way of building a network, and this I'm not going to go through time. I don't have time, but this is just a bunch of software. It's a software only system, basically. Think of it that way. And the other point I want to make is that researchers don't think about is that to do big things, to do big significant things, you've got to work with others. So what do I mean by that? Large things take time, and large things take cooperation. So for us to build, we had to work with all these products from all these companies, and had to integrate them and put them together. This is not what researchers do, but this is beautiful because once you do that, you have something that nobody else has, and you have something that you can. So there's no more sitting on the sidelines. You kind of do it, but it's hard work. That's kind of what I want to say here. It's hard work. This is some pictures of what we built. I can go into detail, but think of this as a mobile 5G system. So you can take this system, power it in, put a network, and you can have 5G right there. This is very, very dramatic as well. This has never been done. This is not about and we built it and we're going to show it. So this is kind of what it is. Here's a little video of it working. That's the AP. And I'm just going to show you very quickly. What he's showing is this is just stuff that is happening to show. I have to click this a few times. That's the problem. And then you will see Dayok. Oops. How to fix this? Anyway, Dayok, you will see Dayok walk in the room with a commercial cell phone. Like nothing. We did nothing to the cell phone. We just bought it. We got the right SIM on it, and you will see that it works beautifully. There's no audio here, so yeah, he's connected to that. I guess. Oh yeah, here's the screen on the side that you can see, and then he's going to have a Teams call with Anuj. He's calling it over the phone. On the right, you can see, and there you go. For systems and networking guys, this is beautiful. It's not HoloLens, I think, but it's beautiful because on top of this, you can build all kinds of things. So that's that. And then the other quick demo I want to sort of show is, is this. This is, you've heard about xCloud. This is to show, this is xCloud running on our network. And this just shows that how the latency sensitive, bandwidth intensive applications can now work on 5G network. And so that we have some performance numbers, but I don't actually have time to show, but it's very, very impressive. Here are some more pictures of like other stuff we have done, putting these antennas on building 99, had students work on it and we worked on it. So it's that kind of work. Okay. These are the two teams that built it. There's one in Cambridge and one in Redmond. For those in Microsoft, you will recognize the name. There are actually quite a few Movicom PC chairs here. Like for example, Bozidar was a Movicom PC chair. I think Yongwang was also associated with Movicom, and there are others too. I'm just sort of not seeing. And anyway, it's on both sides of these on these things. And so we've got two networks that are built. They are both deployed in the campus on Redmond campus and Cambridge campus, and we are actually expanding that to cover the entire Redmond campus. That's the aspiration for us, and that's got nothing to do with product. It's got everything to do with our own learning and running and operating something like that. And so that's going to happen hopefully soon. The other thing, and I'm about to finish now, the other thing to know is that, I talked about revenue generation. So something interesting has to happen on top of this network. So we've actually got our hands into all of these 5 activities. They are sort of the fundamentals on which other application gets built. So from remote conferencing, which you saw, to cloud gaming, which you saw, to AR, VR, or mixed reality, HoloLens, we've actually got a really, really impressive demo of cloud offloading from that. The video analytics part, which I have so much to say, but won't have any time to say today. And then connected vehicles. So we are all dabbling into all of this because we want to make all of this real. And this is real. This is not going to be just papers, and papers come second. And the other thing is, this is just a nice picture which sort of shows that we are making the network very programmable from the operator's perspective, from Microsoft perspective, from developers perspective. I don't have time to go through this, so sorry about that. So this is my last slide. So what I actually wanted to end, I was trying to think about how to end this, and the way I sort of wanted to think is we are, here's some of the stuff we are doing. We are adapting our planet scale network to carry 5G traffic, because what good is a network if, like when they say RAN, you can go 1 to 4 milliseconds in ultra low latency mode, but then your internet is 100 milliseconds or more, 200 milliseconds. So there's no purpose to doing so much hard work in that last edge. So you got to do it across the board for it to really work. So which is one of the things we're doing, because we have this asset and we're working on it. But you're welcome to work with us if you're a student or even a professor or anybody. And then we are obviously looking the thing I didn't cover, we are looking very deeply into hardware, different kinds of hardware. And many companies are coming up with their, Qualcomm has just announced the X100, Marvell has announced, NVIDIA wants to bring their GPU, and then we have, and Intel has its own. So there are lots of these hardware pieces that need to come together, and we are looking at which one to use, because cost is always a factor, and then performance is a factor. So we are trying to build all of this in our labs here and see where that takes us. The edge, and you know about the edge infrastructure. One of the things we're doing is making it much more programmable, and we are trying to. This is my thing, my own personal thing. I don't think edge computing will be co-located in the way it is thought of today and the way we thought about it when we conceived it. I think it's going to be part of the infrastructure piece, which is why I think, and it's going to be everywhere. That is what I mean by RAN being a killer app. So anyway, I'll stop at this point. I have this slide to share with you in all the different languages. Thank you very much for hearing me. I do write blogs. If you're interested in this kind of work, you might want to sort of like, check out some of the blogs. I actually put a lot of thought behind these blogs, and so it'll give you some sense of what it is. But I think at that point, I am going to stop and hang on, and then turn my video on. I don't know how much you can see me because it's kind of dark here. But here I am. Voila. Okay. That's my talk.
Thank you, Victor. So I saw in the screen, I think Professor Li Mo has some question. Maybe you can unmute yourself and ask a question. Yeah.
Right. Thank you. Thank you, Victor. It's a very, very nice talk, very inspiring. Actually, I didn't make it to the MobiCon, but it's very nice to get sort of centralized here.
I'm
Right.
very glad you liked the inspiration, because that's the whole. Anyway, that's great. Go ahead.
All right. I think my question is in the coming sort of a new form of networking, we will have Internet of Things. The data may come in intermittent and from massive devices, and other applications like VR, AR, which has latency sensitive data traffics. So we may expect very different data traffic patterns, and how that impact or what's the implication to your edge RAN in the Azure architecture. I'd like to hear your vision on that.
Yeah, it's a great question. Nobody actually has asked me this, so let me. So this will be the first attempt at the answer. So I think the big powerful thing that 5G are, and I don't want to think get stuck on 5G or 6G or whatever next year is this concept of slicing. And so in slicing, you can actually you can have slices of different properties, of different bandwidth, different delay sensitivity, and different error rates, that kind of thing. You can also have slices on from a secure perspective. So for example, in the US, NSA or an equivalent in China says, hey, I want to use a commercial system, but I want to make sure that my packets are siloed from all the other packets, and they go through certain servers and not the other servers. And so the network can provide slicing as well. So now in the so by the way, slicing is non-trivial to do for operators. Let me just say this. It's intellectually pleasing because it is about resource management, resource block management, frequency management, all that kind of stuff, and scheduling and all the things that we've done. But it's very hard for the operators to understand how to monetize that. But leaving that aside, the IoT thing is also about slices. It's like, you can give a slice to all the IoT devices that are in your enterprise and run them that way. So that's how I sort of think that the data flow of different kinds will be managed on the substrate of network slicing. And that's kind of how it'll all clean up. I don't want to think like, for example, people have LoRa, Sigfox, LoRa, all these things. They operate at different frequencies. So one of the things that's going to happen in 6G space, I think, again, I'm speculating, is that more frequencies will open up. Like this is already that has happened. And those frequencies will be incorporated into the new 5G thing. So for example, if you think about Wi-Fi, that frequency of 5G can work on Wi-Fi. There's nothing that stops it. There's no law, nothing that stops it. So I think as this gets more sophisticated, as they get more, this is where the action will be, because we're not going to have so many networks. It's a hodgepodge. There's so many hodgepodge of networks, and that just sort of like is. So I don't know. I hope it answers your question, but
Yep.
yeah.
Perfect. Right. Thank you very much,
Okay.
Victor.
Of course.
Yeah, thank you.
Any other?
So yeah, I think we can, due to time limitation, we can take another question from Yongqiang Xiong. Please go ahead.
Oh, okay. Thank you very much, Victor, for very inspiring and very wonderful talk. And I have one question regarding the software-defined 5G. So we all know that you once run the mesh network to help the society, the older mobile ad hoc society for their research, and for the Sora, we also follow that tradition.
Yeah.
So I'm very interested to see the fantastic demo for software-defined 5G. You can really run the whole network with all software and to enable the commercial mobile phone for the communications. So I'm just wondering, so whether or not you have similar plan to open that to the whole society, whether or not you will enable the another wave of the mobile research with that platform.
Hats off to you for bringing that question. That's also a different and unique question than I've heard. So meshes were interesting. So we had a different goal with mesh networking. So what the goal, and actually the same goal existed with white spaces as well. The goal was that we wanted to bring down the prices of broadband access to the millions of people around the world. And it was very difficult to do that by just telling the operators and all to deploy because they didn't have money. So we needed to show both. We needed to lobby and we needed to show some muscle. And this is not something I've said in public in the past, but I'm saying it now, which is that the muscle was that, look, if you don't do this, we are just going to create these networks with meshes, and we're going to come after you if you don't do it yourself. So in that sense, mesh succeeded because many areas that didn't have broadband access started to have it. White spaces was also about that, like try to get broadband access. We in fact freed up 180 megahertz of frequencies because of that. So when you say, so in my mind, mesh was not ready for commercialization the way everybody sort of just jumped in. We couldn't control that part. It was just, Microsoft was doing it, everybody was doing it. It was just like, and so we couldn't control that. But even then, some companies have made a lot of money, like the Meraki made, In this particular case, it's different because in this, we are actually looking at a service in a different way. So we are not changing or bringing new things. We're just sort of making it very programmable, very software oriented, and so that there is a lot more innovation that can go in there. The AI, so much work is happening in AI. Somebody has to think about how will it get ingested? Where will it get ingested? So we are actually trying to do that. We're trying to create a framework where everybody else succeeds as well. And it's difficult. The operators actually understand this at the C level. They all get it. Lower than that, but they are very afraid. I mean, they are very big. I mean, AT&T is about $180 billion revenue. They're not going to just move over and just take it. But they are bold and they are starting to take. So that's the thing. I think it's inevitable. This is inevitable and it will happen. And the mesh part might actually come out of this as well once it becomes very software oriented. But I'm not sort of like including that yet because you got so much to do here. But it's a great question. It's a great critique of me too, which is that, hey, you said that was great. Now you're saying this is great. Now later on you'll say something else is great. So that's a legitimate criticism. But the part of the criticism is that the full story, nobody actually knew what it was. So from our perspective, we actually succeeded in mesh. But the world doesn't see it as that, but we do because we got what we wanted. And this is a little bit different. The story here is different. So I wasn't like jumping just because I get excited about things. No, actually, I do think there is something real here. Anyway, good question. Thank you so much.
Thank you.
We can talk more over a beer or something,
That's true. Yeah.
Yeah.
Once the pandemic is over.
Thank you.
Yeah,
I think
yeah.
Due to the limitation, I think we can only took two questions, and Bebe will help us to have a group photo on the keynote and the first session.